All right, thank you, Aaron, and thank you, people of Earth, for coming to this event. So today we're going to be talking about exoplanets, and it's a very rich subject that is rather young as far as actual data goes. Exoplanet is short for extrasolar planet. It is literally just talking about planets that are found outside of our solar system. And so it's a very new subject, and it was very difficult to actually get started. But let's go ahead and start at the beginning and with the age-old questions that actually brought us here. Now, those age-old questions would be dating back to ancient times of, are the stars that we actually see out there similar to our own sun? And it wasn't until Renaissance time periods where we actually were able to definitively say yes. And furthermore, what came around that same time was also asking the question of, do stars have their own planets? Now, that is a question that, again, around Renaissance times was being asked, and I'll let a later note cover that subject. But around 1855, there was an actual attempted observation, or I should say claim, that a planetary discovery had been found by Captain W.S. Jacob out in India, observing with the East India Observatory. Now, 1855 was a start to an interesting pattern of a whole lot of false positives that lasted for around 140 years. People would make a claim of, I found a planet around another star, and it would be debunked, or over and over again that would happen. This led to a interesting interplay of the way people would look at the particular subject of extrasolar planets. People tended to, in the astronomical community, would tend to look at the entire field as there goes another one, another false positive, another person making wild claims, because this, again, 140-year pattern that lasted for quite a while, but now we know that the answer to that question is actually yes. Which leads to yet another age-old question of, are there other planets similar to Earth? Is there another place out there? Is there other life similar to our own out in the universe? This is a critical question, one we do not yet have the answer to, but we are rapidly trying to answer it, and we actually have some technology that we might actually be reaching into the realm of being able to answer that question. So, as I mentioned, this field is very young. How young is it? Well, the first exoplanet discovery actually occurred during my lifetime. I've been following exoplanets for a while now and have seen a lot of interesting things happen. Originally, when they were first discovered, discoveries came in at a very slow rate. Now, a few a year sounds potentially pretty slow, but when you look at the scale of 140 years of false positives, it sounds pretty fast. So compared to now, it was a slow rate. And in order to emphasize this, I will mention a little anecdote about a computer desktop widget. When I first started actually watching and monitoring how extrasolar planet discoveries were going on, there was on NASA's, or the Jet Propulsion Laboratories, website, Planet Quest, they had a little desktop widget you could download, and it would show the current planet count in the lower corner of your screen all the time. And it sat there at around 270-something when I first got it, and it would sit there for a while. I was in college at the time, and some of my dorm mates would make fun of me like, why do you have that? You expect it to change? Well, in the end, it started changing very, very rapidly, to the extent that originally at the time, only about 11 or so years ago, we were actually around 270 planets found outside the solar system. Now we are in the thousands. This is the actual current count from Caltech's database. We can actually see the discovery methods by which each of these sets have been found. You can see pretty dramatically that under transit, you have around 3,000 actually discovered there. Radial velocity around 670, and only a few attributed to them. But I want to spend some time actually talking about 5 of these methods because they're very important for actually understanding how we find these planets. We'll start with that first one at the top that only has found one, but was early on one of the main ways people were actually looking for planets. That is astrometry. And what astrometry is basically when you take a picture of a star, you don't expect it to be moving when you take another picture. It's not going to be in a wildly different place. These are your sort of background. We don't expect much movement, but when we say much movement, we mean some movement is potentially there. And what we see normally is what's called proper motion. Normally, what that would mean is if you were to watch over tens of thousands of years, you would see stars moving away from each other, towards each other, relative to each other. You would see this motion, and you would be able to, by taking multiple pictures, be able to measure those distances, those angular distances, very precisely. And as such, what you actually end up doing for trying to look for a planet is you want to watch for periodic motions. Now, there are some key things that actually make that work. Here's an actual example of what that is. Normally, planets and stars orbit around their common center of mass, so it makes the star actually wobble a bit. And so if you're measuring very carefully the location of that star relative to other stars, you potentially could be able to see it moving around. That is the idea behind astrometry. The big problem is, in order to actually make a star wobble visibly, you need a very big planet that's typically pretty darn close to the star itself. And so, as such, we've found one case where this method of planet detection has actually worked. It has an advantage because it doesn't matter the orientation of that system to be able to work, but again, it has a number of disadvantages that makes it very difficult to actually detect planets with. All right. Now, there's another method called direct imaging. Literally, why don't you just take a picture of the planet? Well, this early on was largely discounted because of the actual very, very small separation between the objects involved. Normally, when you're looking at a planetary system, especially if you're concerned about planets like the Earth, you're looking at separation distances of only like 93 million miles, or rather 150 million kilometers. It's a very small distance on astronomical terms. If we were to compare an actual distance such as how far away the nearest star is, it is around 4.2 light years away, where 1 light year is 1 times 10 to the 12, or excuse me, 1 times 10 to the, yes, 1 times 10 to the 12 meters away. I believe I got that right, or 1 times 10 to the, it might be 13 actually. Yeah. Excuse me, because I'm doing unit conversions in my head. I know it more for kilometers. It's 1 times 10 to the 1 times 10 to the 16 meters. 1 times 10 to the times 10 to the 13 meters or kilometers. Goodness. Okay, now back done with unit conversions. Moving right along. It's a very big number, is what I'm trying to say. Trillions of kilometers away. Okay, now what we're actually saying with that is, okay, we've got a very, very small distance compared to this massive distance. Why would we ever be able to take a picture of it? And in fact, when you're actually trying to image it, you therefore need a very, very high resolution camera, and you need stars that are nearby in order to actually make that comparative distance as big of a ratio as possible. And you also need to actually blot out the light from that star. It's very difficult to actually do that. And what that actually would end up looking like is, say we had a star here, we would actually want to put what's called a coronagraph in front of it and make something very dim, easily visible next to it. It's very hard to get that set up, and there's a few interesting ways of trying to do that, which we'll hear about a bit more later. But we've actually had some success in this regard. We've found tens of planets with this method, and my favorite set actually is seen here in this image. You can actually see 4 different planets in this particular image. You can see one here, one further out there, and one way out here. Now, note the scale of this image. 20 AU is 20 astronomical units, 20 times the distance between the sun and the Earth. And this 20 AU thing is about the diameter of our coronagraph, so we are not able to see anything that would normally be within, say, an orbit of Jupiter, typically with respect to our solar system. So this current system, if that system was looking back at us with the same technology, they wouldn't be able to find anything but Saturn, Uranus, and Neptune. That would be all they'd be looking at out, and they'd actually be found pretty close to that coronagraph as well. So it's very limited in its capability, but it's still a worthwhile and very cool thing to actually see because that's literally another solar system we are looking at. So it's a really cool thing to actually be able to see. All right, so another one is gravitational microlensing. This is a fun, mind-bending type thing because it actually uses general relativity, because general relativity suggests that light should be bent by massive objects. And in fact, we see this all over the place. We see galaxies warping the images of galaxies behind them. We see all sorts of interesting things at the centers of galaxies. But when we're actually looking at, say, a distant star and another star passes in front of it, we can actually see that the star in the distance gets magnified. It gets brighter all of a sudden because of the star passing in front of it. If that star that is passing in front happens to have a planet with it, it will cause some interesting effects on the light, on the way that star is magnified. The way that actually ends up working out, we can see with this diagram. This is our distant star here. It's emitting some nice bright light. Here's our graph showing what we're seeing. And we got to watch really quick to follow it. Here's our moving planet. Here's the Earth, or that's the planet. There's the star. You see a little blip on that magnification. The actual intensity of the light goes up, and you get a little blip because of that planet moving along with the star itself that is causing the microlensing event. Again, this is a very difficult way, and it's a very random happenstance way of actually detecting planets because we don't actually get to set these up. We don't get to just watch for these easily. We have to just look around for stars, see how they're moving, and if we're lucky, we can say, that star is going to pass in front of that star. We should watch it. More often than not, we actually have a survey that's just watching for bright flashes and actually taking images of a large section of the sky, watching for these types of events, and then going back afterwards and analyzing them. And if we get enough warning with a start of a bright microlensing event, a whole bunch of telescopes go and look at it to get a lot of more detailed information. It's a very random event, and it's something that we really have to watch for. It's hard to plan for. Thus, we only have tens of discoveries with gravitational microlensing. In contrast, we have radial velocity. Radial velocity discoveries are wonderful, and they rely on the Doppler shift to actually work, the Doppler effect. If you aren't familiar with the Doppler effect, can I get someone to actually give me the sound of a car driving by? Okay, very good. What's great is you actually, albeit subtly, you actually demonstrated what the Doppler effect is. It is a shift in tone of an object, whether it is going towards you or away from you. So as such, a car approaching you has a higher pitched tone to it, and one driving away has a lower pitched tone. As such, like that. That is the Doppler effect in sound. So what's great about the Doppler effect is it doesn't just work with sound, it also works with light. So what you can actually do with a star is you can take the light coming in, basically do what's been done since the days of Newton and split it into a spectrum. He used a little prism. Now we use diffraction gratings or other things that spread out the light into a really nice rainbow. And what you actually see in that spectrum are a bunch of different features, normally what are called absorption lines. These are little dark lines in that rainbow that are indicative of certain elements at certain temperatures in the star. But if you watch those lines, you might see them shifted to one side or the other, or you might see them actually shift back and forth. And if you see them shifting back and forth, that means you might be seeing something wobbling around in a circle. What I mean by that is take this setup again where we have our star and planet orbiting around their common center of mass. This star will be moving towards and away from us if we view it from the right perspective. And by that, I mean, should be starting. There it goes. Okay. By that I mean, if you view this system edge on, we can actually see that as the star moves away, the light coming from us is red shifted, the waves get spread out, and as it moves towards us, it's blue shifted. The waves of light actually get compressed together, and you can see this sort of diagrammatic action here. It's moving away, those waves get very spread out, and likewise, as it spins back around, you can see it the waves compressed and gets blue shifted. It's ever so slight. This is highly exaggerated, and it's a wonderful system. And as I mentioned, we've found over 600 planets with this method. The majority of the early planet discoveries that were made using this method. That 270 number I mentioned earlier were almost entirely found using this method at that time. Now, there's a big problem with using this in general, and that is, if you're looking at the system from this perspective, that star is just moving around in a circle here. It's not moving towards or away from you. There is no Doppler effect at that point, at which point only certain orientations of stellar systems actually produce any radial velocity, and that's one of the big limiting factors for this particular detection method. All right, similarly, we have the transit method. Now, this method is the most critical method the most critical tool we have in our arsenal of means to finding extrasolar planets. It has been highly successful, and the way it actually works is you just stare at a star, and you try and do it as often as possible, and you just wait to see if a planet goes in front of it. That's basically the idea of the transit method. And that's what actually makes it very hard from an astronomical standpoint. Here on the ground, we miss half the time we can possibly be staring at a star because there's daytime. Daytime kind of makes it hard to stare at a star if the entire sky is brighter than the star itself, or, for example, the star happens to drop below the horizon. Also a big problem. Nevertheless, we can still use this method if we know when we should expect to see a star actually have a planet transit in front of it. Again, that's a rare event, and I'll talk about a lot about the tools we now have to actually predict those things. Now, as I mentioned with the radial velocity method, there's a big constraint on this one. If the radial velocity method needs some angle tilted towards us, the transit method requires an even more specific orientation, because what are the odds that your planet is actually passing in front of your star? That is a very specific type event, and you have to have a very specific perspective to be able to see it. Nevertheless, despite that, this has been by far the most successful planetary detection method to date, with almost 3,000 detections actually confirmed with this method. Now, how does that actually end up looking? I mentioned it's a planet passing in front of a star, and what you do is you constantly monitor that star, you measure the brightness of that star, and eventually, if a planet happens to pass in front of it, you see its light decrease. Now, this is a highly exaggerated curve. Typically, the actual amount of light that is decreased from a star is on the order of less than or about 1%. So you need to have very precise measurements of a star's light in order to actually be able to get good detailed measurements. Okay, well, that's all and good. Do we have some examples of what this might actually look like? Yeah, we do. This example actually is from the Solar Dynamics Observatory. It's orbiting up in I think it's in low Earth orbit, but it's viewing the sun in ultraviolet wavelengths. That's wavelengths that are shorter than normal visible light. All of this light that you would be seeing here is filtered out by the majority of it is filtered out by the Earth's atmosphere, which is great because that's a great way to get a sunburn. So it's good that all of the majority of this light is actually filtered out. Nevertheless, when we're actually looking here, what we're looking at here is the transit of Venus back in 2012. You can see it actually moved across the surface or the face of the sun in that particular fashion. And if we were actually summing up the total light coming from the sun, we would be able to actually make a graph like you saw in the other image. But as I mentioned, there's a big constraint on the system to actually be able to observe something like this. With us moving around the sun and Venus moving around the sun, this event actually happens only twice per century. They happen typically around 6 years apart. So if you miss this, I'm sorry, it's going to be a long time before the next transit of Venus from the perspective of the Earth. So this was a great opportunity to actually get these kinds of images, and we have a wealth of them now. But this is an example of what one might actually look like if you could resolve a planet passing in front of a star. Most of the time, we don't have that luxury. But nevertheless, we can actually learn a lot about what a planet looks like and what its orbit is like when we actually do see transits. For example, compare these two planets, if it will play. There we go. We got a big planet and a small planet. The question is, how much light will be blocked by this planet relative to this one? When it actually passes in front of a star, the larger planet will blot out more light than the smaller planet. As such, if we know something about the size of the star, which we can through a good amount of statistics and other things by looking at all stars in the sky, we can learn to a good extent what the size of the planet should be. And based on the actual amount of time it takes to go across the face of that star, we can learn more about the orbit of the planet. And even when we actually measure multiple dips over the course of multiple orbits of that planet, we can very carefully learn about the actual mass of the planet, which means with the transit method, we can actually learn the density of the planet because we know its size and its mass. And so that's very useful if we want to know if it's a gas giant planet or a rocky planet like the Earth. So that's very important, and it's very helpful to use this method for finding out that information. Okay, so that's a good set of methods to finding extrasolar planets. So now we know how we can actually find some of these planets, but it's worthwhile to actually know the entire story. This is the theoretical way in which one finds the planets, but in order to actually find them, you have to develop the technology, and in order to develop the technology, you have to have the will to do so. And this is a critical and important endeavor, and I want to take a step back to look at the history of the actual first extrasolar planet discoveries, but I personally am not as qualified to tell you about that history as those who lived it. So I'm going to let them do that here. So enjoy this. We will take a step back into this right after this brief documentary. There we go.
The famous Italian monk Giordano Bruno in 1586 published a book in which he said the sun is a star and that the earth was a planet and that other stars certainly had planetary systems and probably even had life. And for that and other radical things that he said, the church burned him publicly. You could say that extrasolar planets was a much hotter field back then.
Exoplanets were almost as silly as looking for extraterrestrials, little green men on other planets.
Seriously, looking for planets was a kind of weird topic.
The whole field had sort of a snake oil sheen about it because over the previous 50 years or so, there had been many, many claims of the first extrasolar planet ever, and the one thing all those claims had in common was that they were wrong.
In San Francisco, California, astronomers Jeff Marcy and Paul Butler were quietly looking for Doppler shifts, changes in the observed color of light from the star.
I literally spent the first 8 years of the program simply trying to improve the techniques involved in making these sort of measurements, mostly totally under the radar. Nobody knew what we were doing and nobody cared.
A ray of hope that it might be possible to detect a planet came with the discovery by Dave Latham and Zvi Mazet of a mysterious object orbiting the star HD 114762.
They announced the detection of an object that they called a brown dwarf. They looked and they didn't see it in a telescope, so if it was a star, if it was 1,000 times the mass of Jupiter, they would have seen it.
To this day, it is not known whether this object is a planet, a brown dwarf, or even a low-mass star, but its discovery emboldened others to continue the search. A different and dangerous approach to planet hunting was underway in Canada. The team of Gordon Walker and Bruce Campbell employed the deadly gas hydrogen fluoride in an attempt to precisely measure Doppler shifts.
And he showed me their setup in Canada at one point. One person would be in there doing the setup, and the other person would be outside of the room looking through a porthole with 2 gas masks. And his job was, if something went wrong, throw on a gas mask, run into the room, throw the gas mask on the other guy, and drag him the hell out. Any good science should have an element of danger. There should always be at least the vague hint of death involved. Otherwise, you're not really on the cutting edge. They really pioneered the whole field, just a spectacular achievement.
We're all here because of the work that they did.
In 1992, another incredible discovery piqued the interest of astronomers looking for exoplanets. But these new exoplanets were not orbiting a regular star. They were orbiting a pulsar.
Two very small bodies got detected at Arecibo by Wilsham and his colleagues, and they really got us scratching our heads. So we call them pulsar planets.
Wilsham and Frail is somewhat of a special case because I don't think anyone really doubted that these were planets as much at the time, but they were planets around a bizarre object, a pulsar.
But they really were the first two bodies to orbit a dead star, not a currently shining star.
The formation of planets is an incredibly robust process. And that's what that discovery told us, and we missed it because we didn't understand it.
We should have understood that planets don't come in ones, that they come in systems. But we were still focused on finding the very first planet.
Halfway around the world in Geneva, a pair of Swiss astronomers were hard at work developing a different technique. Their instrument relied on fiber optic technology, and they used it to turn their eyes on exoplanets.
My first day of work, I got this booklet from Michel that was the ultimate knowledge of data processing of spectroscopy. There was almost nothing at that time, and that's it. And we had to do this instrument. And we designed this practically without much support from anybody else because the other people felt that this was not interesting.
After a few months, already at the end of '94, we got a signal of variability for several stars, not only one, several stars.
We realized very rapidly that the instrument could be far more precise than we thought. So I started with a couple of stars a bit more intensively, and 51 Peg was one of them because it was bright. And very rapidly, 51 Peg had a very weird behavior.
On one side, we were absolutely sure of the quality of our measurement. All the signal was in favor of a planet, but it's evident it was a so unusual planet.
And I really thought at that time, oh, there is something really bad in the software on the instruments, and I better to figure out because otherwise my PhD would be compromised.
Over the next several months, the two astronomers checked and rechecked their data. The problem was no one could imagine a giant planet with such a short orbit.
So we came back in July, this time together with Michel, very excited. I say, okay, let's see whether the conclusion that we had with the first bunch of data we had still holds.
The real moment where we had the confirmation of the reality of 51 Peg, it was really a planet, was in July '95.
First data, just on it, we say, okay, just luck. Second data, still on the curve, we say, okay, well, 2 is far, there's still 2, it's not enough. The third one was still on it, following a track, and then we say, well, let's just wait the fourth to be really, really sure, because it was so embarrassing conclusion, that planet, that we really want to make sure that was real.
We got the good period, the good amplitude, and so on. So at the time was really the time for the celebration. Before we were not sure that it was a planet.
I mean, there is a real planet. Believe it or not, there is no theory to predict that planet, but there is a planet there.
Following days of rumors circling the globe, at a conference in Florence, Italy, the news unofficially leaked. A Jupiter-sized planet had been discovered. This massive planet was making a complete orbit of its star in only 4 days. How could that be?
Suddenly there's this 51 Peg, which is a Jupiter-sized planet, but in a 4-day orbit. And people knew that was impossible. Jupiter-like planets orbit at like Jupiter and Saturn orbital distances.
Back in San Francisco, Marcy and Butler, by mere coincidence, had 4 consecutive days of reserved telescope time at the Lick Observatory, the exact amount of time needed to confirm or debunk the claim.
We hit the star very hard for those 4 nights. We reduced the data as quickly as we can. We were blown away. We saw exactly the signal that Mayor and Colo had announced.
Confirming my data, to me, was just the best gift I could have had, because I said, oh, fine, so all the work I did is right.
Here in San Francisco, the discovery was dramatically verified just this past weekend.
October 19th, 1995.
What may be the discovery of new planets outside our solar system has created enormous excitement among astronomers.
The confirmation was made before the official announcement of the discovery itself.
It went completely out of control.
Everybody was discussing of this new object except us.
By tradition, scientists have their discoveries peer-reviewed by other scientists for accuracy.
I was one of the referees on the paper. There were 3 referees. Normally I think they only do 2, but this was so big that the Nature editor, Leslie Sage, was being very careful.
Because of the situations, Nature was very strict. They say, well, look, guys, if you talk to people, then we're not going to publish your paper.
So it's only after 1 month or something like this that I receive a message from Nature that, okay, no, you are relaxed from the embargo.
Because the discovery was just too big, just far too big to follow the usual scheme that is required for a scientific paper. As soon as you start talking about that, I mean, everybody wanted to know about this.
51 Peg B is a real planet, no question about that.
As soon as we detected 51 Peg, he had on his data plenty of something like that. You just need to look at it.
At this point, we hadn't analyzed all our data. We had 2 computers, and it would have literally have taken us 5 or 6 years to get through all of the data. So literally about a half a dozen different groups said, you know, we've just received these new computers, and we're not going to use them for the next several months. You want to dump your jobs on it.
Within 2 months, 2 other Jupiters circling around their stars were found by Marcy and Butler, and the floodgates of planet hunting were now wide open.
You know, from no planets at all to the point where we're discovering a new planet every month or even sometimes every week. And almost all of the planetary systems that we found were very different from the solar system, weren't even similar in the least bit.
I remember asking at a meeting, you know, how long do you think this will go on? And I think Michelle Mayor said, oh, maybe, you know, another 5 or 10 years, and then the game is over. Fortunately, the game just got a lot more exciting.
After getting my PhD, I became aware of this fellow at NASA Ames Research Center, Bill Baruch.
I would see him at all these meetings. They were very small meetings back in the day. And like he'd literally be by himself out having dinner, so we would join him and chat about things, and he was very persistent.
Bill walked around the halls, and whenever the Ames managers saw him coming, they turned and walked the other way.
Bill Baruch wrote a paper in the 1980s that described the transit method. When that planet passes in front of the starlight drops by a tiny, tiny amount. And by measuring the brightness of the star, minute by minute, we can detect planets going in front of the star, and we call that the transit method. And detectors that could measure that precise drop in brightness didn't exist yet.
To be successful, all one needed to do was build a photometer 1,000 times better than anyone ever built one. But I'd worked on the Apollo program, I'd worked on other programs, so that's not really that scary. You just need to get down to brass tacks and find out what's required and build it. There just is no way of finding small planets in orbits like that of the Earth unless you go into space. You must go into space.
He kept getting shot down by the review panels for various reasons, and each time he'd fix the reason and go back a second time, and they basically said it's not going to work. Well, Bill Baruch didn't bother reading that report, or at least did not take it to heart. Kept on his crusade to show that transit detection should work.
He was able to demonstrate in the lab that he could measure the precision required to find Earth-sized planets orbiting sun-like stars.
Some people call it stubbornness, but the point is I knew it would work.
So he proposed and reproposed, and eventually he conceived of a Discovery-class mission that was later called Kepler.
It was 25 years between the date of publication and the date that Kepler actually launched.
1-0 and liftoff of the Delta II rocket with Kepler on a search for planets in some way like our own.
Kepler just delivered so much tremendously new things we never even conceived of. And the things that were on our wish list, Kepler found for us.
This data was being displayed for the first time on the computer monitors. And there was the transit of that Jupiter-sized planet, and the data was like beads on a string.
Kepler has transformed our understanding of exoplanets. What Kepler was designed to do specifically was to go after terrestrial or rocky planets that are in closer orbits to stars. We now know from the Kepler data that planets like the Earth are in fact common in the galaxy, and that's something we fundamentally didn't know before Kepler.
The first exoplanet was already diverse, and Kepler continued to find more and more planets that didn't fit the norm, both in size, in composition, in distance from their stars. So when you think about how many stars there are in our galaxy, there are a few hundred billion, and if each one has one or maybe more, we're looking at a few 100 billion planets.
To accomplish something great, you have to have persistence.
To succeed in exoplanets, we have to be very ambitious and very bold.
Kepler's impact was extreme, certainly more than I'd ever imagined. It's basically opened up an entire new era of astronomy.
Now that we know that the galaxy is teeming with planets, we are ready to go to the next chapter of planetary exploration.
I truly believe that the 2020s are shaping up to be a golden age for observational astrophysics. You know, we have these amazing telescopes like Tess, the Transiting Exoplanet Survey Satellite. We have WFIRST, which is this Hubble-sized telescope that can see 100 times as much of the sky in each image. We have the James Webb Space Telescope, which is, you know, the largest and most powerful telescope we've ever built. You know, the reason that we can even dream about that and create something like that is because of the success of Spitzer and Hubble and the previous great observatories.
I'm looking forward to space-based missions where they're going to have Coronagraph technology and maybe even star shield technology in order to image exoplanets by blocking out the light from stars.
And we have the next generation large 30-meter class telescopes on the ground, which are going to be coming online in the 2020s. But the question that has me most excited about the future of astronomy is to answer the question, are we alone in the universe?
Finding evidence of life on an exoplanet, finding an indication of a living world, is within our reach.
What is life? Life is a process to transfer information from one generation to another.
Everybody is interested in the search for planets, the search for places that remind us of home.
We're looking for some hint of our origins, where we came from, and exoplanets may very well provide that context.
There may be more habitable real estate out there beyond our solar system than we once thought.
I think we're naturally curious to find out if there are other conditions in the universe that might be similar to our own. And finding exoplanets around other stars is the first important clue.
The search for planets is a search for life. And even though we didn't really say that out loud, that was always in the back of our minds.
In such a short time frame of knowing only the 8 planets here in our solar system knowing that, by and large, we're the only place where we would expect to find life. We've looked out and once thought Mars might be habitable. We found nothing there. We looked and found, well, we found nothing of life like ourselves there. We see some potential for places in some of the moons of the larger gas giants where some form of life might exist, but it's expected that it's probably at best microbial. The perspective up until recently of having looked around and found that we are it is something that until very, very recently, only in the last decade, really, have we actually been able to allow our perspective to say there should be so many planets out there that should be habitable. Billions of planets in our galaxy with enough of a large set that the statistical improbability of having something in a similar setup to our own system, of having a planet of Earth-like mass and an Earth-like orbit, there's enough stars out there that that's entirely plausible to be found within our galaxy. We have a lot of statistical information, and this is what is wonderful about the prospects of what we can actually see. We can actually now say there should be something to look for specifically. There are a few missions talked about in there in some detail, but I'd like to take a closer look at some of those to figure out what we actually can see with regards to this particular notion. So we'll start first with the Kepler Space Telescope. It was what Bill Baruch was working on in that documentary, and it is, again, responsible for the identification of most exoplanets that we've seen today. Its actual original planet candidates are now up to around 4,496. Now that is actually, what that means is the telescope would stare at a section of the sky, see some things that it thinks are planets, let people on the ground know that it's found something that could be a planet, and then people would follow up with ground-based observations to confirm it. Of those, the total confirmed planet discoveries are currently at 2,652. Now, those numbers come from, again, that same database I told you about, but those numbers aren't lower because all the rest were false positives. There were some false positives, but by and large, they just simply have yet to be confirmed or disproven. So of that large set of 4,496 stars, there's still a good number that we have yet to just find out that they actually are stars. That means that Kepler, though it's moved on to another stage of its mission and is eventually going to end its secondary mission as well, it still has provided a ton of data that we still have to work through and find new planets in. Now, again, it found most of these by staring at one spot in the sky. The way that actually looks is all of these little specks you see on this image are extrasolar planets around stars. And if you look carefully, where you can actually see that this ring is 100 light years out, 200 light years, so on. So the vast majority of planets are either in this area, we see a few further afield, but the majority are in this cone. That cone is actually where the Kepler Space Telescope was looking for the first few years of its mission. And if we actually look from the perspective of Earth, that cone looks a bit like this. Now, I told you to make note of that funny shape that was in the video. That shape was actually the CCD, the imaging chip of the main camera on the telescope. It was bent in order to compensate for the fact of the actual focal length being not providing a perfectly flat surface. But that cone that you actually look at is shaped exactly like the CCD imaging chip. There are a series of chips, and you can see the gaps even in between those chips. So there are likely planets right in between all those little imaging chips that we just weren't able to see because we can only have such a large surface area on that imaging chip. So that's really what ended up providing the vast majority of those stars. Now you can see some, even here, some of the other discoveries from other missions scattered about, but by and large, this huge density of extrasolar planets are all just in one tiny section of the night sky. And you can see there's some constellations around it. You have Draco here, and you have Hercules up here, and you have Lyra is hanging out over it. So tonight, when you look out to the east, around 10 p.m., you might start seeing Hercules rising, and then the rest of that will follow shortly thereafter. But again, very small patch of sky. What's great about that system is how long it was able to provide very good information there. Unfortunately, in 2013, the second of its 4 reaction wheels, and what those wheels do is they provide a set of angular momentum to ensure the camera points in one particular direction. And when one of those failed, okay, we can compensate with the other 3. When the second one failed, the camera could not be kept on the same area of sky permanently. And what that actually resulted in is what was believed at the time to potentially be the end of that mission. Fortunately, it was not. It was actually the start of K2, or Kepler 2. And what that actually did was, we can't permanently look at one area of the sky, but we can focus on a certain area of the sky for a few months at a time. And what that ends up looking like is we end up with this funny path along the ecliptic plane. In the night sky, this actually forms a straight line all the way around the sky itself. It is the plane of the Milky Way, or not the Milky Way, the plane of the solar system is the ecliptic plane. And so we can actually observe for a while in one direction with K2, which is wonderful because it's already given us hundreds of planetary candidates. Now, that was one mission that revolutionized our view of planets and really our view of the universe and where we actually see real estate. This was the very first really dedicated transiting space mission. There's another one coming up. That is Tess, the Transiting Exoplanets Survey Satellite. It works in a somewhat different method than the Kepler Space Telescope. Instead of staring at one point in the sky, it will stare at many different regions. It will actually end up observing much of the sky. And what it will do, instead of Kepler, which looked deep into the galaxy and deeply looked for a whole bunch of different things, it's actually going to focus right here in our neighborhood. It will look at near and bright stars. In fact, it'll be looking at stars that are between 30 and 100 times brighter than those observed by the Kepler Space Telescope. Now, we aren't going to have sound for these, so I'm going to attempt to narrate these because the issue that we were having with sound was not completely resolved, so we'll see what happens here. Oh, we have sound, never mind.
The Transiting Exoplanet Survey Satellite is NASA's newest exoplanet mission. Led by MIT, Tess will find thousands of new planets orbiting nearby stars. During its 2-year survey, Tess will watch a wide variety of stars, looking for signs of planets ranging from Earth-size to larger than Jupiter. Each of Tess's cameras has a 16.8 megapixel sensor covering a square 24 degrees wide, large enough to contain an entire constellation. Tess has 4 of these cameras arranged to view a long strip of the sky called an observation sector. Tess will watch each observation sector for about 27 days before rotating to the next. It will cover the southern sky in its first year, and then begin scanning the north. Tess will study 85% of the sky, an area 350 times greater than what NASA's Kepler mission first observed, making Tess the first exoplanet mission to survey nearly the entire sky. Because Tess's observation sectors overlap, it will have an area near the pole under constant observation. This region is easily monitored by the James Webb Space Telescope, which allows the 2 missions to work together to first find and then carefully study exoplanets, expanding our understanding of worlds beyond our own.
Now, the James Webb Space Telescope is basically the successor of the Hubble Space Telescope. And the reason those poles, those polar regions actually matter to James Webb Space Telescope is because the orbit of the James Webb Space Telescope will always be able to observe those regions. It will be able to observe the rest of them at some point in time, but those 2 points are directly outside the plane of the orbit of not only the Earth and the Transiting Exoplanet Survey Satellite, but also James Webb Space Telescope. As such, those two regions never pass behind the sun. So by focusing a lot of observation in those regions, we can have a lot of nearby planets found at a better rate than some of those ones down near the orbital plane of the solar system. Now, that's a great overview of where it's looking, but how it's looking is worth knowing too. And as such, we will take a look at that in one more brief video, if it will go for us.
Tess, the Transiting Exoplanet Survey Satellite, is NASA's newest exoplanet mission. Led by MIT, Tess will find thousands of new planets orbiting nearby stars. To accomplish this, Tess will fly in a special highly elliptical orbit that maximizes the amount of sky the spacecraft can image. Once Tess has launched, it will expand its orbit until it can get a gravitational assist from the Moon. This slingshot will move it into a stable orbit that is tipped at about 40 degrees from the Moon's orbital plane. Tess orbits Earth in exactly half the time it takes the Moon to orbit once. This feature helps stabilize the spacecraft's orbit against tugs from the Moon's gravity. Tess will spend most of its 13.7-day orbit observing the sky. As it approaches Earth, Tess will rotate and transmit all its accumulated data to scientists on the ground. Over 2 years, this will allow Tess to study nearly the entire sky and potentially find thousands of new exoplanets.
So the actual setup there is very interesting. The Kepler Space Telescope was one big mirror that absorbed a lot of light. The Tess spacecraft is not much bigger than this podium. It's actually very small, and its cameras can be handheld. What is impressive about that is what that means, what that says about what it's looking at. You're not looking at very, 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 very faint objects. You're looking at brighter things. And so Tess's targets will be bright, they'll be nearby, and they'll be very favorable for follow-up observations here on the ground. Now again, it will provide us with a wealth of new candidates, potentially worth following up even with small observatories. And yes, that's a hint. This is something I'm really looking forward to attempting to actually get the data from and actually utilize here at Rancho Mirage Observatory. Whether or not we'll be able to actually get really good data and follow-up, that's yet to be seen, but that is something that is a worthwhile goal, and it is very likely that we should be able to get some very good images of, well, not direct images of extrasolar planets, but again, the reason this is very good for a observatory like ours is because this is the transit method. We can follow up with further transits of these planets whenever they happen to occur, because when you actually get candidates, and even after they're originally discovered, we can actually follow up and further constrain parameters about planets by observing them transit in front of their stars again and again. So it's a very worthwhile thing that I am very excited to potentially use our observatory here for. So one other very, very exciting thing about this particular mission, everything you saw, Kepler mission was all past and well, still present in some ways. There were a number of things talked about in the future. This is still in the future, but is the very near future. It is launching tomorrow at 3:51 p.m. Pacific Daylight Time. So if you're interested in watching the actual launch of this, I recommend going online, and if you actually just Google Tess launch, you will probably find live streams, or you will likely be able to see it on NASA TV as well. So this is something I'm very excited about. I'm leaving you with this cliffhanger here because we don't know what's going to happen with this, and it is the cutting edge of what we are able to see, and it is going to tell us truly about our neighbors here. It will tell us what planets are nearby outside of our solar system. We know of a few already, but we are about to know of a lot more. Thank you.